In this video, we are going to present another proof of infinitude of primes, and this proof is due to Paul Erdos, and he is using nice arguments with analysis and number theory. So let us first assume P1, P2, P3 etc. be the primes in increasing order. So when I say this, do not think that I'm considering infinitely many primes as a sequence, right? P1, P2, P3, etc. Then it is already done. So my aim is, I don't know where it ends, where it stops, right? But I'm just starting to write P1, P2, P3 in an increasing order, right? So more easy way to do this, let us call this set as a set of all prime numbers having script P, as we can have a denotation like that. And my aim to prove that the summation 1 over P, right, P varies over script P, diverges. If I can prove this, right, then as a consequence I can prove the primes are infinite. Okay, and that's very simple. If I can prove this, and if I assume primes are finite, then this sum will convergent, which is contradiction to the fact we are just going to prove, right? So we can just assume the contrary, that this sum is converges, right? So what happens if it converges? If it converges, then the definition of convergent tells that the sum is equal to a real number, right? Actually a positive real number, because the summands are all positive, right? So now if this sum convergence means, what is the meaning of convergence of a series? That means its partial sum is convergent, right? Here the partial sum I can write like this: xn equal to summation j going from 1 to n 1 over pj, right? Converges, right? The partial sum converges. Now we look back to the convergence of the sequence. We can write like this: the epsilon definition, for every epsilon, or for any epsilon positive, I can find a k which is a natural number, such that for every n greater than or equal to k, the distance between the sequence and the limit can be made smaller, right? Even less than epsilon, right? Okay, now we have assumed that it converges, right? So let us take epsilon positive to be half. Then there is a k where for every n greater than or equal to k, the inequality is true, right? So in particularly n equal to k, this inequality is true, right? That means what? Modulus of xk minus l less than half. This xk is nothing but we replacing k by this n. That means it's going from 1 to k 1 over pj, minus, because it is a limit L, then we can replace this L by the complete sum, which is summation j greater than or equal to 1 over pj, right? So complete sum. And so this sum is basically this would be larger, right? Because it is a big sum. This is up to k. So if you take this up to k summands from this, you will get a negative that can be avoided by this modulus. And finally what you will get? You will get the tail from k plus 1 to we cannot say infinity, after k plus 1. That sum we will get. That is sum from j greater than or equal to k plus 1 over pj, which is less than half. So for this inequality, if you multiply both sides by an arbitrary natural number, capital N, then you can show that summation j greater than or equal to k plus 1 is very immediate from this. N over pj is less than n over 2, right? Now next is coming the series ingredient to the proof. So we are defining a number np, where we can first look at this set. It is the hash denotes the number of elements in this set, right? That's what np. So what is this set? We call this set nb bar later, right? So this set is the positive integer less than or equal to n, where m over pk plus j belongs to natural numbers for some j greater than or equal to 1. That means if one of the pk plus j divides m, then m will come inside this set, and it will be counted in the number np, right? So basically it is a number of positive integers less than n or equal to n, where it has a prime divisor of this form, right? Now for our convenience, let's call pk plus j, pk plus j is big primes, let's say, okay, and pj from j less than or equal to k, that means p1, p2 up 3 pk, we can call small primes. And then nb is a number of positive integers less than n which are divisible by at least one big prime. That's what they're telling, right? For some j, okay, at least one big prime. And now ns I'm going to define, which is the positive integers less than or equal to n, where m over pj belongs to n for some j less than or equal to k, but not j greater than or equal to k plus 1. That means these are only, these m's inside this is only divisible by small primes. So here I have forgot to place a hash here, so you can have a hash because ns is a number of elements in this set, right? Yeah. So yeah, now that means what? ns is the number of positive integers less than n which are only divisible by small primes, or divisible by only small primes, right? So important. So from this we can see that these two sets under this they are mutually exclusive. So we can observe one important thing, that nb and ns, they are all less than or equal to n. That's a count of less than or equal to n, right? Number of, so that will be equal to n. We can prove that very easily. For this we consider the set nb bar. Now this is a set nb bar associated to nb. This is set of all natural numbers which is less than or equal to n, where n has at least one big prime divisor, right? And ns bar is a set of all natural numbers which is less than n, or n has a only small prime divisor. And it is very easy to observe that these union are definitely equal to n, right? For that we can prove the first thing from left to right to left. If we take an element from 1 to n, right, then t is a prime divisor, definitely. So either it is a big prime, okay, then if it is a big prime it will come inside nb bar, so it belongs to the union, right? Okay, right. Now if it is not divisible by any big prime, then our assumption, right, our assumption is every natural number has a prime divisor. So it must have a prime divisor which is in small primes. That means it belongs to ns bar. So that is also true. So nb union ns bar equal to 1 to n. This inclusion is very easy, because if t belongs to the union, definitely it's less than or equal to n, and it's a natural number, so it will be greater than 1 also, equal to 1 also. So this is true, right? If this is true, that's and also if they are mutually exclusive, then there is no intersection between them, right? Okay, so suppose an element belongs to that intersection, what is the meaning? It is divisible by a big prime and it is only divisible by a small prime. That's not that's weird, right? So the intersection is empty, union is 1 to n, so definitely nb plus ns is capital N. But we will show that there exists a natural number n such that this inequality is strict, that is nb plus ns, nb plus ns is less than n, is not equal to n. right? We'll prove such an n exists. If we can exhibit such an n, then we will get a contradiction. Now, how do we do that? So first of all, we need to estimate the number nb. So for this, we can observe if n is a natural number and p is a prime, the integer part of n over p, floor function n over p, that counts the number of multiples of p less than n, right? It's very easy to see because, right, because the multiples of p are of this form, p2, p3, p4, p, like that it will go, and it is n over p, integer part of this, times p. And after this, and now n over p plus 1 p, that will not be that will be definitely greater than our n. Why? Assume that suppose this n over p is a natural number, right? Then p will cancel, you will get n, right? You will get n, and after a few go, you will not get n, right? It will not be less than n. So this is the maximum number, right? Which is a multiple of p, right? This is the maximum number. So this counts that, right? So n over p is the number of multiples of p which is less than n. Okay, how do we estimate this now? So this is our inequality. We got this. So how do we got this? We prove that mb less than or equal to summation j greater than or equal to k plus 1 n over pj. Okay, so this is very easy. So the right summation, look at the summons. So first summand is n over pk plus 1, and I mean integer part of n over pk plus 1. So that counts number of multiples of pk plus 1, right? Okay, in the second summand counts number of multiples of pk plus 2. So this completely counts number of multiples of big primes. So definitely the count nb, all numbers we counted in nb will be in this, right? Yeah. Now the thing is, it is less than or equal to that, and why it is not equal, right? Why it is not equal? Why it is less than? The possibility of less than. So see, if m is a number less than or equal to n, and suppose pk plus 1 divides m, then by the definition of nb, we know that we can count it once because it is divisible by at least one big prime. It is pk plus 1. But the same number, if it is divisible by pk plus 2, we are not going to count it again, right? Because of already we have counted. That is the way we have designed that set, right? Okay, so we don't want to count it twice. But that is not the case when we come to the right of the inequality. In the right, the n over pk plus 1 already counted the number m, but if pk plus 2 divides m, it will again count, right? It will again count in the second case also, right? Because if pk plus 2 divides m, then m is a multiple of pk plus 2. So that will, so the second summand also counts this number m. So basically in the right of this inequality, this sum will count same number twice. So that will definitely make it larger than the left. And we already proved that this inequality, right, without this integer symbol. You can also see this is a greatest integer less than this number. So definitely this would be less than that sum, so less than n over 2. So this works. So that means nb is less than n over 2. That's our estimate. nb is less than n over 2. Now let us estimate ns, which are the numbers which are only divisible by s. So here we need a little bit more careful thing, because here we are assuming n is equal to is of the form ab square, and this a is the square free part of that number, and b square is a square part, and we will make an estimate for this number of square free parts and number of square parts, and we will make it an estimate for this. So what is mean by square free part? So if you a number is a square free if it is not divisible by square of a prime number, right? Yeah. So okay, a square part is which is a square of a number, a divisor which is a square, that is square part. Now we can make a bijection for this square free part. So you know, when square free part it will be it not divisible by a prime square. That means any prime come there, it will not repeat. So that means square free parts are basically like product of different primes, right? 2 primes, 3 primes, right, like that. And quickly we can make a bijection of this number of square free parts and number of subsets of P1 to Pk, this set, because each subset corresponds to one product, right? Suppose for example P1 P2 P3 corresponds to P1 P2 P3 times, so this is a square free part. So all square free part is this form, so it corresponds to each of the subset, right? So 1 is a square free part, so it corresponds to phi, right? So the number of square free part is equal to the number of subsets of small primes. So basically it is 2 power k, because there are k small primes. So we got an estimate number of square free part is 2 power k. Now we have to estimate number of square parts. So number of square parts. So what is a square part? So square part is a divisor of n, right? Okay, a divisor of n. Okay, that's a very important thing. And also we can make an estimate of b. Okay, that b if b square is a square part, then b can be less than or equal to root n, right? And we will make it more clear. For this, what do you mean by a square part? A square part is it is a square factor, right? It is a perfect square factor of n. Okay, fine. So we consider all the sequence of squares, right? So it is 1 square, 2 square, 3 square, like that is going, right? Now the square part of a number n will lie in this set, right? In this sequence, definitely. And look at this, the way I have arranged it: 1 square, 2 square, 3 square, root n square, root n plus 1 square, like that. Now look at this. A root n square itself is n, right? Now if you square root n plus 1, you will not get n. So that means these numbers cannot be the factor of n, right? Because they are all greater than n. And also these numbers is less than or equal to n, because root n square is n. So root n minus 1 square is less than or equal to less than n, right? So it is it can be a factor of this. Okay, root n minus 1 square can be a factor of this, right? And it is a square part if it is so. So how many square parts are available? So these are all less than n, and these are all squares, possible squares. So all the square parts of n will lie in this set. So what is the number of possible here? 1, 2, 3 up to root n. So there are root n possibilities are there for a number of square parts of. Okay, yeah. Now root n is less than or equal to capital root n, right? Then root of capital N, right? That means the possible square parts, right, is at most root n. Okay, whatever the number you take n, right, that n is less than or equal to n, so n can be n minus 1, n minus 2, it can be n also. So maximally it is n. So all the square parts, right, all the square parts will lie less than root n. I mean it will be the maximum number possible is root of capital N, right? So there are at most square root of n square parts possible. That means we can estimate this inequality. ns is less than or equal to ab square, right? So a is 2 power k possibility, square parts are n root n. Then ns is less than or equal to 2 power k root n. Okay, now we can estimate the sum. So now nb plus ns is less than, right? Why it is less than? Because nb is less than n by 2, right? 2 power k root n plus n over 2. Now if you can prove this sum 2 power k root n less than or equal to n over 2, we are done, right? Then it is completely less than n. That means if you rearrange this, what do you have to prove? You need to find out a natural number n such that you can multiply both sides by 2 and divide it by root n. Then you get this in equivalence, like 2k plus 1 less than or equal to root n. If you prove this, if you prove that there is a natural number n, then we are done. So for this is easy. It admits equality, so you only need to find a natural number n such that 2k plus 1 equal to root n. For this it is easy to you can take the square of 2k plus 1, right? N equal to 2k plus 2, right? If you make a square root, you get 2k plus 1. Okay, so if you put this n here nb plus ns is less than n, which is a contradiction because we already proved nb plus ns equal to n, right? Yeah, so that means the summation 1 over p diverges. Now if p were finite, then this will be a finite sum which contains the fact that we just proved. So the primes are infinite, right? So you can ask any doubts in your comments, and you will get the notes in the blog also, right? Okay, thank you.